Hi, in this video we're going to look at the biochemistry of life, including ionic, covalent, and hydrogen bonds, acids, bases, and salts, and some about chemical reactions. So let's look at some examples of covalent bonds. Here we see the chemical methane. It's a type of molecule held together by covalent bonds. By molecules, we mean that it's a neutral group of atoms held together by covalent bonds. Overall, there isn't a positive or negative electrical charge to it. The covalent bonds means that the atoms involved are sharing electrons to follow the octet rule. So by itself, carbon has 4 valence electrons. It needs 4 more. By itself, an atom of hydrogen has 1 valence electrons, and it just needs 1 more to fulfill the octet rule. Both of these elements are nonmetals, which is another characteristic of the chemicals involved in a covalent bond. In this diagram, we can see just the valence electrons involved bring the atoms together, they share the electrons, and we can abbreviate it as a single line instead of the dots for electrons, and that gives us the chemical methane. It's a very common hydrocarbon. Here we see a slightly different molecule, but it's still held together with chemical bonds. This molecule is called ammonia, with 1 nitrogen and 3 hydrogens. By itself, a nitrogen atom has 1, 2, 3, 4, 5, 6, 7 electrons altogether. The first 2 have gone into the first orbital. That leaves 5 electrons in the outer ring, and like before, each hydrogen involved has 1 electron. By sharing the electrons between them, by putting them in both orbitals, the hydrogen atoms get 2, which satisfies the octet rule, and the nitrogen atom gets 8 valence electrons, which satisfies the octet rule. So there's 3 sets of covalent bonds. Each of these is a single covalent bond symbolized by 1 line. Now, ammonia and water together make a slightly different chemical called ammonium hydroxide, which is a very toxic chemical. And what we do with our bodies, we get lots of nitrogen, and our body converts that ammonia to urea, a different chemical which is much less toxic, seen down here. And then our body processes urea into urine to get rid of it. Now consider another example of a covalent bond. You have 1 atom of oxygen, 1 O, but then you can have what's called molecular oxygen, 2 oxygens together. This is how we find oxygen in our atmosphere. The 2 oxygen atoms each have 6 valence electrons. Oxygen's atomic number is 8. It has 8 protons. A neutral oxygen atom has 8 electrons, 2 in the first orbital, and the other 6 in the valence or outer shell. So together, by sharing 2 sets, we have a double covalent bond. Again, both of these are nonmetals, which is another characteristic of the elements involved in covalent bonds. We can see them by 2 sets of dots shared, or it could look like 2 solid lines shared. Here's a double covalent bond in carbon dioxide. The carbon is sharing 2 sets of valence electrons with this oxygen and 2 sets with that oxygen. The 2 pairs of electrons are being shared with each carbon to oxygen bond. All this happens to satisfy the octet rule. All the involved atoms end up with 8 valence electrons. Here we can see a more complicated diagram. As we start to involve tens or dozens of atoms, we have much more complicated numbers of covalent bonds forming. So we have the chemical sucrose. There's 12 carbons, 22 hydrogens, and 11 oxygens involved in this chemical, which makes up most of table sugar. So that tells us the relative numbers of each atom of the different kinds of elements, but it doesn't really tell us how they're formed together. And that would involve more complicated chemistry. You couldn't look at this formula and realize that this shape was happening. You'll notice at times in this shape, they chunk together several hydrogens and oxygens and carbons because there's just not room to show the full spread of the chemicals. Likewise, when looking at diagrams like this, people well versed in science realize that carbon is very frequently the chemical backbone of these elements. And that's why they don't even show the carbons involved. They just make them the vertices. The place where the different bonds are meeting is assumed to be a carbon. So when you see a more simplified diagram like this, it's highlighting that there are these little side groups. There's an oxygen and a hydrogen. And it doesn't matter that the H comes first or the O comes first, because remember, these are supposed to be 3D models that we've put onto a 2D flat space. And likewise, they don't show that there's a bond between the hydrogen and oxygen, but it's there. It just happens so commonly that people who understand what they're looking at know that it's assumed to be there. So not every bond is always shown, depending on what the diagram is trying to highlight. Here we see caffeine. How would you know this is covalent? These are all nonmetals, and they're all sharing electrons. You can see there are some double bonds in here. There's actually a mistake. This nitrogen has 1, 2, 3, 4 covalent bonds. That wouldn't honestly work. We saw earlier, looking at ammonia, that nitrogen tends to form 3 sets of covalent bonds. But other double bonds do work and fit together. So, what else is happening? A cup of coffee has about 125 milligrams of caffeine in it. That's 3.88 times 10 to the 20th power of molecules, individual molecules of caffeine. That's 388 followed by all these zeros. We use scientific notation to abbreviate that. Here's ephedrine. It's another chemical held together with covalent bonds. Now, ephedrine's a banned substance because only changing a few of these molecules around gives us the illegal narcotic known as methamphetamine. You can see a different way of showing it called a ball and stick model. That helps represent the chemical compound by the different atoms, and there's some color coding. Red for oxygen, blue for nitrogen, black for carbon because it's very common, and white for hydrogen because it's also very common. We can also see here that carbon can form rings. Carbon is often known as the backbone of these molecules because of all the places where it forms the central linkage. Not all the time. For example, here's a link with nitrogen, but many times in organic chemicals, carbon is the main molecule or the main kind of element involved. We can look at another detail about covalent bonds. They can be classified as polar or nonpolar. Remember, in covalent bonds, the electrons are being shared, but the different kinds of elements have a stronger property of attracting the electrons. Now, if the electrons are shared equally because it's 2 of the same molecule or 2 of the same element, like carbon and carbon, the electrons they're sharing in this cloud of electrons are pulled equally between them. So there's no stronger atom that has more electrons, so it's nonpolar. There are no electrical poles. On the other hand, between oxygen and hydrogen, there is a stronger pole for the oxygen to attract the electrons to it more strongly. And so there is an unequal sharing of the electrons. This is shown by a slight negative charge. the electrons hang out over here slightly more than over here. Because oxygen wants them to fulfill its octet, there's a stronger pull for it. Now, it's not a full electrical charge, it's only a slight electrical charge. So they use the Greek letter delta, that's a lowercase delta from Greek, to show that there's slightly more electrical charge that's negative over here, because the electrons that are negative are hanging out over here. This leaves the hydrogen part slightly positive, on the other hand. So this is what's called a polar covalent bond. In chemistry, polar substances are attracted and mix with each other. On the other hand, nonpolar substances are attracted and mix with each other. So water is polar, and so is salt. And so those two things mix easily. On the other hand, things like vegetable oil is nonpolar. So water and vegetable oil would not mix because one is polar and the other is nonpolar. Here we see the covalent bonds involved with water, a polar substance. Hydrogen by itself has one valence electron. Oxygen needs two more. By sharing a covalent bond with two hydrogen atoms, we have the substance of water, and that has covalent bonds. They're sharing electrons. Now we can move into ionic bonds. Here we see sodium chloride, the most typically viewed and known and familiar ionic substance. You have a sodium ion, and it is transferring or trading an electron to a chlorine or chloride ion. This sodium has lost an electron, giving it a charge. This chlorine atom has gained an electron, giving it a net electrical charge of -1. We call it a chloride ion. They're ions because they do not have equal numbers of protons and electrons. By trading the electrons, the sodium ion and the chloride ion achieve the octet. Sodium doesn't need to share anything, it wants to get rid of one. Chlorine doesn't need to share anything, it just needs to gain one entire electron. This happens in a repeating pattern, leaving sodium chloride as a crystal type structure with repeating units of the sodium ion and the chloride ion. So ionic bonds involve an attraction of oppositely charged ions to each other to form an ionic bond. They are not sharing electrons. Ionic bonds are weak compared to covalent bonds. Water can dissociate them or pull them apart and dissolve ionically bonded chemicals together. Overall, ionic bonds tend to form crystals. Here we can see again that sodium chloride involves an ion of sodium and an ion of chlorine that we called chloride. They're ions because the number of protons and electrons are not equal. So the electrons are transferred. I've said all this before, it's just showing it again that there's a sodium that has lost an electron, making it positive, and a chlorine that has gained an electron, making it negative. They have both achieved the octet. If we zoom out, we can see how the initial instability of these substances leads to a more stable substance. By themselves, sodium is very reactive in nature. Likewise, chlorine, pure chlorine, is a toxic substance to humans. It messes with our lungs. But together, it makes the stable substance, sodium chloride, that we eat as table salt. In fact, it's one of the few mineral substances that we eat. Mostly we're eating living things like plants and animals. But salt is a mineral. It's like a rock that we eat. It's actually worth mentioning some of the history of salt because it's so interesting. In ancient Rome, salt was used as money. It led to the term salary. The Roman workers were paid in salt to flavor their food. Salt is also a very useful preservative to keep food from spoiling. And so you salt your food, it prevents microorganisms from causing it to rot away. The company Morton Salt is a multi-billion-dollar company. Since the early 20th century, it's had the advertising slogan, "When it rains, it pours," meaning that even in hard times, it would be easy to get Morton Salt. They don't just make salt for food, of course. They use it for people's water conditioning, industrial and agricultural purposes, and even road use. It's always good to realize the popular brands we're all familiar with are owned by multinational corporations whose names we're not always familiar with. It's good to see the business side of this. It was owned by a company called Rohm and Haas, but then Dow Chemical bought that company, and Morton was sold to a German chemical company called K&S in the early 2000s, around 2009 or 10, I believe. But it just goes to show the things we take for granted, the popular brands we know, are linked to much larger corporations. It's always good to know where your food comes from. Now, there's also a social aspect to salt. Coastal areas get lots of iodine in their diet because they eat seafood and there's iodine in the ocean salts, and so those people have a common, easy to get source of iodine. However, across the world, iodine deficiency causes developmental problems and health problems for billions of people. It can also cause goiter problems because iodine is concentrated in the thyroid gland in our throat. Also, if there's radioactive fallout, one part of the fallout that people can breathe in can be radioactive iodine that can lead to thyroid cancer. So we have to be very aware of iodine in our diet. If we look at the periodic table, we would see that iodine is in the same group as chlorine, the halogen group, and they behave in chemically similar ways. So, table salt is sodium chloride, but we can also include iodide in there, and it will work similar to how the chlorine works in salt. So in the 1920s, copying the pattern set down by some other countries, the United States started adding it to salt, which was much more easily available, and that helped people living far from the oceans to get enough iodine in their diet. It's a thing that we all take for granted now, but realize 100 years ago we didn't have the same food systems in place, and this solves a problem that people aren't even commonly aware of now because the system has been in place for almost 100 years. We can look at other ionic materials. Here's potassium iodide. It involves an ion of potassium, which is a metal, and a nonmetal iodine. Another characteristic of ionic bonds is that they involve the combination of elements that are metals and elements that are nonmetals. Sodium is a metal, and chloride is the ion version of chlorine, which is a nonmetal. Like other ionic compounds, they are trading electrons to give both atoms a full octet. You also have potassium bromide, a similar chemical that is used to treat the rare form of canine epilepsy, which affects dogs. Another example of an ionic compound is sodium fluoride, a metal and a nonmetal. Sodium is completely losing an electron to a fluorine atom, making a sodium ion and a fluoride ion. This is a medication used to prevent tooth decay and is a source of a fluorine tracer in PET scans. Those are called positron emission, I forget what the T is, but some kind of an imaging scan for our body. You can have multiple ionic bonds. In calcium fluoride, the calcium atom is losing 2 electrons, 1 to each of 2 fluorine atoms. They all get the octet, and they are ions in this case. Here you have aluminum oxide. There's 2 aluminums, and they give up electrons to 3 oxygen atoms. How would you know this is ionic? Aluminum oxide, by the way, is part of what makes up rubies and sapphires. Rubies also have some chromium ions involved, and sapphires have some iron and titanium, which makes sapphires blue. So, we have to consider the total charges of these. The 2 aluminums have a +6 charge to donate, and the 3 oxygens have a -6 charge to accept the electrons. So it's like finding the lowest common multiple, a +3 and a +3 and a -2, -2, -2. So that's slightly more complicated, but it helps extend our thinking about ionic bonds. There are even polyatomic ions. Certain atom groups covalently bond with each other, and there is a group of them. Overall, the group has a charge and is called a polyatomic ion, many atoms together having a charge, such as ammonium. This is not nitrogen hydride. This is a commonly known group called ammonium. Nitrogen and hydrogen are involved in the group, and overall the group has a positive charge. Or you could have nitrates. These names are not on the periodic table. You have to be familiar with them as examples of groups, and the overall group has a charge on it. You can also have combinations of both covalent and ionic bonds. So within disodium phosphate, we have 2 sodium ions bonded with a group that has 2 negative charges. Some parts are covalent, the phosphorus and oxygen, and the oxygen and hydrogen, and some parts are ionic, from the sodium to the oxygen. This is a chemical used in foods and medicine. Here we see sodium bicarbonate, commonly known as baking soda. Now, sodium bicarbonate comes from reactions of acids and bases. It's not a salt in the same way that common table salt is, but it's a chemical salt. It's a name for a general class of things that form when an acid and a base react. So sodium bicarbonate is a chemical salt. Not just table salt, not the salt we eat, but a variety of a chemical classified as a salt. So we've seen covalent bonds and ionic bonds. We're going to look for a little bit at acids, bases, and pH before we wrap up by looking at hydrogen bonds. Now, in water, there are a bunch of H2O molecules dissociating. They come apart and they come back together repeatedly all the time. Breaking apart water can give you hydrogen ions, hydroxide ions, or hydronium ions. These are what you get as the H2Os come apart and come together. When all these things exist in balance, it's neutral drinking water that we could drink with no problems to our life. However, by mixing different chemicals in with water, we can have more of one of these. When one is unbalanced, say more hydrogen ions or hydronium ions, it's an acid. If we add different chemicals, there can be an unbalance or an imbalance to the amount of hydroxide, making it a base. We talk about base and acids by measuring them with pH. To understand pH, you need to understand a thing called moles from chemistry. A mole is a way of counting things. The same way a dozen means that there's 12 of something, or a pair means that there's 2 of something, a mole means that there's 6.02 times 10 to the 23rd, a large amount of something that helps us count many, many tiny chemicals or atoms. So 1 mole of a substance in 1 liter, or a volume, enough to fill a large glass, is a unit of concentration called 1 molar, symbolized by an italicized capital M. So you have to know what moles are, and that tells us what molar means, and we symbolize it with italicized M. So with concentration, it's like, for example, how salty is something, or if you were adding food dye, how intense is the color of food dye added to water. To measure how acidic or basic something is, we have what's called the pH scale, which is based on the molarity of hydrogen ions on a logarithmic scale. So because it's logarithmic, it means a change of one number on the pH scale represents a tenfold change in hydrogen ion concentration. Likewise, moving by 2 numbers on the pH scale represents a 100-fold change in hydrogen ion concentration. Now, to maintain homeostasis, our bodies use substances called buffers. They help slow down changes in pH. So if you eat some lemons and you have lemon juice, which is a form of citric acid in your body, it doesn't throw your whole body's chemistry out of proportion. We have buffers. Buffers neutralize the effects of acids and bases and slow down changes in pH. I'm sorry here. So here we see hydrochloric acid, HCl. When we add it to water, we have an excessive amount of hydrogen ions or hydronium ions in the chemical resulting. So we have pure water, but adding hydrochloric acid to it means there's much more of this now, and it's an acidic substance. Hydrochloric acid is the acid found in our stomach. It's stomach acid. On the other hand, you have bases. Bases form hydroxide ions, and here's a common base, ammonia, NH3. By adding this, the substance that results gives us lots of OH. I'm sorry, it should sort of be over here, the way it's organized. We can see it in this diagram. Ammonia takes an hydrogen off of water, and now we have lots of excess hydroxide. Here we see the pH scale from 1 to 14, from very acidic to very alkaline. Remember, moving one space on this means there's a tenfold change in hydrogen ion concentration. So if you go 1, 2, 3 steps on that, it means there's a 1,000-fold increase, and the lower you go, the more hydrogen ions there are. The higher you go, the less there are. Sulfuric acid is battery acid. Carbonic acid results when you mix carbon dioxide and water. Acetic acid is in vinegar. DNA is actually a kind of acid, and in our proteins there are amino acids. On the other hand, common bases include sodium hydroxide, which is Li, sodium bicarbonate, and ammonia. Now finally, to talk about the last kind of bond are hydrogen bonds. Hydrogen bonds are the weakest of the chemical bonds. They exist as an attraction between polar molecules. They're not sharing or trading off electrons, but they're very important because they give water the properties that make water unique and important for life, and it helps determine the shapes of important molecules like proteins and DNA. In this diagram, we can see hydrogen bonding between water molecules. Here we see one water molecule, and within that molecule there are covalent bonds holding these guys together. But they're polar covalent bonds, and hydrogen has a slight positive charge, and oxygen in an adjacent molecule of water has a slight negative charge. And so the hydrogen bonds are these quick forming and quick breaking, brief little chemical reactions between the hydrogen of one chemical and a negative part, often oxygen, of a nearby or adjacent molecule. So within water, it's covalent, but between water molecules, it's hydrogen bonds. A little bit more to wrap things up. Chemical reactions make and break these bonds. The structure of the atoms determines how they're going to react. When we go from atoms to compounds, we get emergent properties. Water can do things that neither hydrogen or oxygen can do. Here we see a chemical reaction. 2 hydrogen and an oxygen react to form, there should be a little arrow there, 2 H2O molecules. The reactants are the 2 molecules of hydrogen and 1 molecule of oxygen. Even though it doesn't say 1, we assume that it's there. An arrow, which my PowerPoint isn't showing, means that a reaction is happening, and it leads to the products, 2 molecules of water. The 2 out front means there's proportions of twice as much of this as 1 of that. It scales up. We can start saying 2 molecules of this to 1 molecule of that to 2 molecules of this. But that, just like a recipe for food, scales up as long as the proportions of 2 to 1 to 2 are held. What's going on in the atoms from those numbers means that there's 2 hydrogens, 1 oxygen, and it reacts to form an H2O. Finally, here's a more complicated reaction. It's the overall reaction of photosynthesis. 6 CO2s and 12 H2Os react to form 1 glucose, which is C6H12O6, 6 oxygens, and 6 water molecules. So that's a larger chemical equation, but throughout all of this, you'll find that the number of oxygens over here is equal to the number of oxygens on the other side. So we've talked about covalent bonds, whether they be single or double. I should mention there's also triple bonds possible. We've talked about nonpolar and polar covalent bonds. We've talked about how these bonds can be shown in different kinds of molecular models. Ionic bonds, hydrogen bonds, acids, bases, salts, pH, and chemical reactions. There was a lot in this, but thanks for watching. I hope it helps.